right, picking up where we left off, let's write this matrix in row echelon form. We need ones down the diagonal. I'm gonna put a little arrow here to myself. All right, I'm gonna inspect this matrix. I see a 1 leading off the top row, so I'll leave this row where it's at. I need a 0 here. So I'm gonna focus on the second row right now, making some changes. And then when I'm done working on the second row, I'll make the third row have a 0, 0 with a 1 here. Okay, 1 or 2 of these we'll have to do, probably just 1 at most on any kind of assessment. Okay, row 1 doesn't change. Okay, now I want to focus on changing this 3. I need a 0 here. So I'm going to take advantage of this 1. I'm going to multiply this 1 by -3 and add it to what's in row 2. So I'm going to record that here. This was just my little arrow saying I'm moving this way. So in front of row 2, I'm going to say -3 times row 1 plus row 2. So -3 times 1 is -3 plus 3 is 0. -3 times 2 is -6 plus 7 is 1. Oh, that was nice. -3 times -1 is 3 plus -5 is -2. -3 makes this -9 plus 14 is 5. Well, we got lucky changing that 0 and then also getting a 1 here. So actually I'm going to drop down to this row 3 right here, and I'm going to focus on how could I take this -2 and make it a 0. So I'm going to go back to row 1, multiply it by 2. 2 times 1 is 2, add it to -2. I could replace with a 0. So I'm going to take row 1, multiply it by 2, and add it to row 3. So here I'll get a 0. 2 times 2 is 4. 4 plus -1 is 3. 2 times -1 is -2 plus -3 is -5. 2 times 3 is 6. 6 plus 8 is 14. All right, so I need to do a little more work on row 3. I need this 3 to be a 0 and this -5 to be a 1. So I'm going to head over this way. At least row 1 and row 2 are good. All right, let me put my plan together. Okay, I don't want to change that 0, but I do want to make that 3 a 0. So I'm probably going to work with multiplying something into row 2 and then adding it to row 3. If I multiplied this 1 right here in row 2 by a -3 and added it to 3, I'd get another 0. So my plan is to row 2, multiply it by -3 and add it to row 3. So let's come over here. 0 times -3 is still 0. 0 plus 0 is still 0. That won't revert to any other number. It'll stay 0 if I work off of row 2 that has that 0 there. -3 times 1 is -3 plus 3 is 0. -3 times -2 is 6. 6 plus -5 is 1. Ooh, we got lucky again. -3 times 5 is -15 plus 14. -15 plus 14 is -1. So we did it. We wrote this matrix in row echelon form. We have ones down the diagonals. It's not reduced row, but that's okay. Reduced row would be too much more work. All right, why do we care about this? Here's why. Let's say that this was an augmented matrix, meaning these are our constants and this is x, y, and z. Let's change this back to a system of equations. So if this was x plus 2y minus z equals 3, and this was 3x plus 7y minus 5z equals 14, etc., and I wanted to solve that system of equations, if I could get the augmented matrix in row echelon form, and this is an equivalent matrix to the first one, I would work off of this equivalent matrix, and I would say, well, I have x plus 2y minus z equals 3. I have 0 x's, 1 y minus 2z equals 5. But look down here at the bottom row. No x's, no y's, but we know that z is equal to -1. If I could take this matrix and put it in row echelon form and then convert it back to a system of equations, this last row is going to help me know one of the answers. So here, I've got z equals -1. It would be easy to do back substitution to get both y and x. So for example, if I know z is -1, I'd go up here to this previous equation, and I'd say, okay, y minus 2 times -1 equals 5. So this is y plus 2 equals 5. Subtract a 2, and there you go, y equals 3. Now that I have both y and z, it wouldn't be difficult at all to go back up to the original equation and get x. So x plus 2 times 3 minus a -1 equals 3. So what is that? X plus 6 plus 1 equals 3. So x plus 7 equals 3. Subtract a 7, x equals -4. So my solution would be -4, 3, and -1. That would be the ordered triple that would satisfy a system of equations that has this augmented matrix. And that's the idea of where we were going to. So finally, putting it all together. The method of elimination can be applied to a system of linear equations in more than 2 variables. When elimination is used to solve a system of linear equations, the goal is to rewrite the system in a form to which back substitution can be applied. Consider the following 2 systems of linear equations. Consider this system of 3 linear equations in 3 variables. If I were to take and write an augmented matrix and put it in row echelon form, and then once I got there, put it back to a system, that would result in this. And then it's easy to solve from here. If I know what z is, 2, I can solve for y. Once I know y and I have z, then I can come back up here and put those numbers and get x pretty quickly. All right, this whole process that we've been working towards getting to, and what we're going to do in these next 2 examples, is called Gaussian elimination. It says use Gaussian elimination to solve the system of equations. That means convert to an augmented matrix, put it in row echelon form, put it back into equations, and then back substitute. All right, so we've got the equations here. We've got the augmented matrix. Now it's up to us to put this in row echelon form. I think I have a little room here, so I'll at least do a step over here. I like the top row. It has a 1 in it, so I will record it over here. It's not going to change. I do know I need a 0, 1 here and a 0, 0, 1 here, so I'll work on row 2 right now. Notice that if I just added what's in row 1 to what's in row 2, I would get a 0 right here in this position. So let's just add simply row 1 to row 2 and replace row 2 numbers with that sum. So 1 plus -1 is 0. -2 plus 3, oh, that's nice. That's a 1. 3 and 1 is 4, and this is a 7. Might as well go ahead and do some work over here on this bottom row. I need a 0 here, so I need a 2 to go to a 0. I guess I'd multiply row 2 by just +2, because then I could add it to row 3 and get a 0. So I kind of always look back here and go, okay, that's going to be -2 plus 2, that's 0. 2 times 3 is 6, plus -5 is 1. 2 times 1 is 2, plus 5 is 7. And that's -4 plus 17 is 13. All right, I'm going to come down here. I've run out of room. Okay, I'm not going to change row 1 or row 2. They're good to go. Okay, so looking at row 3, I need a 0 here. I need a 0 here, so that's our next target. Well, if I take row 2 and multiply it by -1 and add it to row 3, then that new number would be 0. So going back to the first 0, -1 times 0 is still 0. 0 plus 0 is still a 0. You certainly don't want to change that to anything, you know, other than a 0. You want to keep it a 0. -1 times 1 is -1 plus 1 is 0. -1 times 4, -4 plus 7 is 3. -7 plus 13 is 6. Almost there. Re-record lines are rows 1 and 2. All right, 0 is good, 0 is good. That 3 needs to be a 1. So I'm simply going to divide this 3 by 3 to get a 1. So I'm going to take everything in row 3 and divide it by 3. So 0 divided by 3 is still 0. Same. 3 divided by 3 is 1, and 6 divided by 3 is 2. All right, we're going to convert these back to equations. So if we think about these being our answers or constants, and we have 3 numbers to the left here, that means we have x, y, and z, which we did up here. Zero x, 1y plus 4z equals 7. 0x, 0y, 1z equals 2. So we're actually doing this example right up here. All right, we know z is 2, so now let's find y. So y plus 8 is 7, subtracting 8, y equals -1. Now we got to find x. So I'll use the top equation. A little cleanup over here. So x, remember this is plus 2. This is 8. Subtract an 8 and I got 1. So our ordered triple, which is the solution, is 1, -1, and 2. Alrighty. I am actually going to do one more example. If you're good, that's great. You don't have to stay on for example 2. I'm going to do one more example of solving a system of linear equations using Gaussian elimination. If you need it, great. If you don't, you guys can, you don't have to record it. I'll finish up this video with this example, and then I'll do another short video on the last part of these notes. Okay, so for those of you guys that are staying on here to join me, let's go ahead and change this system of equations to augmented matrix. Okay, I don't like the 3 up here, so I'm going to interchange some rows. I think I'm just going to interchange row 1 and row 2. So I'll leave row 3 alone. And out here, I'm just going to, in between these 2 rows, I'm just going to show row 1 switched with this double arrow with row 2. You could certainly put row 1 down at row 3 if you want. It doesn't matter. Okay. I need this 3 to be a 0. So I'm going to keep row 1. So I'm going to multiply row 1 by -3 and add it to row 2. So -3 times that, we give negative 3 plus 3 is 0. Negative 3 times 1, negative 3 plus 1 is negative 2. Negative 3 times that is negative 6 plus 2 is negative 4. And, don't know that. Negative 3 times 19. Negative 57 plus 31. Ugh. Negative 26. All right, I'm going to go ahead and take and work on row 3. Take a little time to work on row 3. So if I multiplied row 1 by negative 1 and added it to 1, I get 0. So row 1 times negative 1 plus row 3. So that would be 0. Negative 1 plus 3 is 2. Negative 2 plus 2, 0. And negative 19 plus 25, 6. Okay. Boy, I see a couple of things we could do here. Boy, there's a lot of different ways you can go with this. I could actually add row 2 to row 3 and get this to be a 0. But I still need to change that to a negative 1 or a positive 1. So many different ways. Okay, row 1's not changing. I will go ahead and divide row 2. I'll go ahead and target and make this a positive 1 right here. And I'm going to do that because I see that all these numbers are even. And if I took what's in row 2 and divided it by negative 2, all these would be nice numbers. So negative 2 divided by first of all, 0 divided by negative 2 is 0. Negative 2 divided by negative 2 is 1. Negative 4 divided by negative 2 is 2. And negative 26 divided by negative 2 is 13. All right, so row 2 is good. I'm going to go ahead and bring over row 3 the way it is, because otherwise it's going to get complicated. Okay. Row 1 and 2 are good. But I need to change that number to a 0. So I'm going to look up above into row 2. If I multiply row 2 by negative 2 and then add it to row 3. Oops, putting that in the wrong spot, aren't I? Negative 2 times row 2 plus row 3. So 0 times negative 2, 0, 0 plus 0 is 0. Negative 2 plus 2 is 0. Negative 2 times 2 is negative 4 plus 0. Negative 4. Negative 26 plus 6 is negative 20. All right, and the only thing I need to do here is make that negative 4 a positive 1, so I'll divide by negative 4 into this row. So row 3 divided by negative 4, because 0 and 0 both divide into negative 4, leaving 0. That'll give us 1, and that'll give us 5. All right, converting back to equations. 0x, 1y, 2z, 13. 0x, 0y, 1z, so z is 5. So z is 5. That's nice. Okay, so now we've got to find, we know z, we got to find y. This will be 10 to subtract from 13, so y is 3. Let's find x. X plus, where I'm at, x plus y, so x plus 3 plus 2 times 5, which is 10, equals 19. So add those two together, that's 13 to subtract to 19, so x is 6. So 6, 3, 5 is our ordered triple solution. All right, so hopefully that extra example might have helped you kind of work through the row echelon piece of all of this.